solving inconsistent systems of three planes. We are going to have 4 examples here, and actually we'll talk about the first one because it being the most difficult to recognize. Case 1 is when you have 3 planes that intersect at 3 different lines, okay? And we have 3 planes that intersect at 3 different lines. It's a lot of stuff to solve. None of them are obviously parallel, and we'll talk about this situation and how to recognize it. Case 2 is we have 2 parallel planes, okay? And then a third one that is not parallel. And then anytime we have 2 parallel planes that are not coincident and a third plane that's not parallel, it's impossible to have one consistent answer. So there are technically 2 answers to this. And we know how to do this. We know how to solve the intersection of 2 planes, right? But all I really want us to do is to be able to recognize what this is in space. Our third case, we have 3 parallel lines. We just have to check to make sure. There's obviously going to be no consistency here. And finally, case 4 is we have a pair of planes that are coincident but parallel to the third one. So there's an infinite amount of solutions here, but no solutions with the third plane. We're just going to talk about how to recognize these. Jump over the first question. So we have our first question here. The first thing we want to really do is point out things that are parallel. Okay? That's not how you spell it, but there you go. Parallel. The reason being is because only case 1 is the only one that doesn't deal with parallel lines. Okay? As soon as we have parallel lines, we need to check if we have scalar multiples of each other, and then they'll really give us an idea of what we're looking at. So before we do any math, let's check this stuff. So we take a look. Because these are the scalar equations, we know we can find the normals to these by just looking at the coefficients in front of them. And if a normal is parallel to another normal, that means the planes must be parallel also. So we quickly take a look here, and I'm just going to write out the 3 normals. Okay, so normal 1 is 1, -1, 1. Normal 2 is 1, 1, 2. And normal 3 is 1, -5, -1. Okay, so quickly at looking at this, none of these are parallel. That eliminates case 2 to 4 in ours, okay? Because all of those deal with a parallel line. And in consistent system, it also rules out 3 planes all on top of each other, okay? So what we're looking for now is either a point of intersection, a line of intersection, or many lines of intersection. We're going to start with our math here. We'll subtract our values. I'll take equation 1, and I'm going to take equation 2 and multiply it by -1, just so we have x minus y plus z equals 1. Negative x minus y minus 2z equals 2. And I'll take equation 1 again, and equation 3 times -1. X minus y plus z equals 1. Negative x plus 5y plus z equals -1. Okay. Did I do that all right? Oh, no, I didn't. This should have been negative. Okay. We'll find out equation 4 and 5 here. Equation 4, these eliminate when we add. These become -2y. These become -z, -1. These eliminate when we add. This becomes 4y. We're okay? Positive 2z and 0. Okay? So we have 4 and 5. Okay? What we're going to do next is stack 5 and 4 together to eliminate, let's say, the y variable. So I'm going to take equation 4, and I'm going to multiply it by 2. So I get -4y minus 2z equals -2. And equation 5 is 4y plus 2z equals 0. So I know it's looking like we're going to start off with a lot of math here. But when we add these together, this becomes 0y, this becomes 0, z, and this becomes negative 2, which means we have essentially values of y or z that are equal to 2 over 0, which don't exist. Okay, so there isn't an infinite number of solutions here. We have an inconsistent system, and because none of the normals are parallel, that means we must be dealing with case 1, where we have 3 lines that represent the intersection of all 3 planes. Okay? So that's how we recognize case 1. And really that's the most work there is to any of these, is recognizing case 1. We'll jump to another one. Let's take a look at the normals of each of these. The normal of 1 is 1, negative 1, and 2. The normal of 2 is 1, negative 1, and 2. And the normal of 3 is 1, negative 3, and 1. Already, by looking at it, we have identical normals, which means these are parallel. Okay? And if those two are parallel but not coincident, because these values aren't the same, that means we have a plane where at least one is on top of the other. So no matter what the other plane is, it's not going to have one consistent answer. Okay, we're probably dealing with this one, which I think was case 2? 2? Maybe it was 2. Just look back and see. Okay, so this was, we'll say, case 2. Okay, and the following case after that, we would just have coincident ones, so we'd find a scalar multiple of 2, and one that's not right. So an idea of that would be, I'll make one up very quickly. If we had x minus y plus z equals 2, equation 1. Equation 2, x minus z plus, minus y plus z equals 2. And 3, 4x minus y plus 2z equals 3. Right here, these are identical planes, so that'd be plane 1, plane 2, all in one space. Okay? And, oh, sorry, this one has to be parallel to it. So we look for something like this. So we have the normals, again, all being the same, but this one not being coincident, so we have a third plane on top. And I think that's case 4. In case 3, would we have 1, 2, 3 planes, all parallel, but none of them coincident. Okay? So really, there isn't a lot of math to be seen in this one. We just have to really take a look at the normals for inconsistent systems. The only one that really requires a bit of math is when we get an inconsistent system that creates a triangular prism. We have to get to the point where we realize there is no single answer to this. And because none of the normals were parallel, we have an inconsistent system.